Hi everyone, thanks for joining me today. As a reminder, this session is actually a re-recording of a session that Create for STEM did for Oakland County to share some information about our curricular offerings. And so today I'm going to be sharing with you a little bit about the interactions curriculum. Um, so thanks again for joining. So my name is Angie Kolinich, and I am a former Lansing Public Schools teacher. I taught high school science, engineering, and I coached robotics for many years. And now I work for the Create for STEM Institute. I was lucky to be on the Interactions curriculum development team. And so now I do work supporting teachers who are using interactions in their classrooms really across the country, and I'm available anytime if you have questions about interactions, but hopefully what we share with you today will answer some of those questions for you. So today what I plan to talk with you about is just give you a little bit of an introduction to the Interactions project. We'll talk a little bit about some of the design principles behind the development of our curriculum. We will provide some examples of our units and show you how students move throughout the units to gain deeper understanding of those three-dimensional performance expectations and the physical science standards for the NGSS. We'll talk about some of the research results coming from that Interactions project. And previously we had time throughout these presentations for question and discussion. And while we won't be able to do that today due to this being a pre-recording, again, just know that myself and many others at Create for STEM are available to answer your questions anytime. So a little bit about the Interactions project. As you know, Create for STEM, we're not a publishing company. We are a curriculum, or we are a research and development institute at Michigan State University that really focuses on shifting science education for K through 16. So we have researchers who are really focused on undergraduate education. And then my role and the role of others in Create for STEM is really to develop high quality curricular resources, professional learning, three-dimensional assessments to really support the shift in science education that the K-12 framework calls for. And so just to speak a little bit about that, the shift in science education that the NRC kind of called for in 2012 really asks science educators and science education to shift from having students learn about scientific ideas by participating in lectures, reading textbooks, and answering questions on worksheets to figuring out their science education or making sense of phenomena using the three dimensions that are listed in the performance expectations. Essentially, we want students to develop really deep knowledge in use so that they can apply the things that they learn in their science classes to other phenomena they'll experience throughout their lives. And this vision was detailed in the K-12 framework for science education, and the next generation science standards and the Michigan science standards that come from that are both really based on the vision that's presented in this framework. And so that brings us to the Interactions project. Dr. Joseph Kraychuk, who is the director of Create for STEM, was actually one of the lead writers for the physical science standards for the NGSS. And so the Interactions research project was actually funded in 2012, which preceded the release of these standards. But because Dr. Kraychuk was so deeply involved with conversations around the development of the framework and the standards, we were able to begin work on a curriculum that really embodied those standards. We designed the Interactions curriculum to be for these new standards, to be a sample or model curricula that teachers could use. But we also wanted to learn some very important things about students and how they learn. So the actual main goal of the Interactions project was to develop and test this model curricula to really support students in understanding how submicroscopic interactions govern chemical and biological processes. And what that means is that we really hope to support students in presenting understanding of how submicroscopic interactions, or things that they cannot see happening, really cause observable phenomena. So they cause the things that we can see. There was some early research out of Michigan State University that showed that students who weren't doing well in undergraduate chemistry, even if they'd had AP chemistry or honors chemistry before, this was one thing that they really struggled with, is making the connection between things that they cannot see and things that they can see. So we figured that this was such a cross-cutting concept in science. You know, we also ask students to do that in biology with photosynthesis and earth science with many other things. If we could really help them in making these connections in a 9th grade physical science course, maybe they could move through their other science courses more quickly and gain a deeper understanding of those phenomena. And so we set out in 2012, really starting to develop this curricular product that would support students in doing exactly these things. We had intended for interactions to be taught at 9th grade as a physical science course, and that students would transition into biology after the completion of interactions. And so you'll see that a little bit in our performance expectation selection, the ones that we chose to focus on for this course, and the units and how they progress. And so during the development of our curricula, we had a couple of principles that we really focused on. So we wanted this curriculum to use project-based learning as an instructional model, to focus on the figuring out of large observable phenomena, to support the integration of the 3 dimensions in having students make sense of these phenomena, and to support student connections between those observable phenomena and those unseen forces and interactions. But quickly, as we started to move through the project, we realized that just the development of a curricular package wasn't enough. And you know, we put a lot of work into this curriculum, using research in the learning sciences to guide our development of it. But just the curriculum wasn't enough. We also needed to develop high quality 3-dimensional assessment items to really learn what students were learning over time. But also, because of the monumental shift that NGSS and our interactions curriculum presented, we also needed to develop a really robust system of teacher support. So supporting teachers in understanding the how and why behind our curriculum, so that they could best use it and best make decisions about how to use it in their classrooms with their own students in their own context. So over the course of 5-6 years, we would write curricular materials and assessments. We tried them out in classrooms in Michigan, in California, and we took feedback from those teachers and from the students and from video and other data analysis, and made modifications to the curriculum over time. So around 2017, when the project ended, we had a pretty good quality set of materials for 9th grade physical science. And so our hope was that these materials would really help students meet these 3-dimensional learning goals as presented in the framework. So if you haven't had a chance to read the framework for K-12 science education, I really suggest it as good reading material, particularly around the grade level and content for which you teach. But essentially, really braiding together the science and engineering practices, cross-cutting concepts, and disciplinary core ideas all together, all simultaneously, to be able to describe observable phenomena. This was our goal with this curriculum. And so using project-based learning became a really important aspect of our curricular materials too, because it is an instructional model that over many years has been refined and continues to be refined based on new knowledge coming out of the learning sciences. And so essentially all of our lessons and units and interactions follow a similar sequence, where students will experience a phenomena that then hopefully prompts them to generate some questions about that phenomena that they can explore. They then explore those questions using these 3 dimensions that we just talked about: their science and engineering practices, cross-cutting concepts, and disciplinary core ideas. And all of our lessons and units really end in one of 2 ways. Students will either explain the phenomena, develop a robust scientific explanation for that phenomena, or sometimes they, we don't know enough to be able to fully explain it, but what we do have is evidence for the development of new, deeper questions, which then leads us into the next lesson. So this is kind of the structure that governs all of our lessons and units within the interactions curriculum. We're not going to spend a lot of time here other than for me to say that the development of these materials goes through a really, really rich and robust process that starts with really identifying which performance expectations we hope to tackle. And again, in the development of interactions, we selected those performance expectations that we felt students at 9th grade could really explore at a conceptual level, and that really supported the development of a deep understanding of bridging unseen submicroscopic forces with observable phenomena. So that's kind of how we selected those performance expectations. Then from there, we go into really in-depth unpacking, and then brainstorming the phenomena, development of a storyline, etc. There's a similar process that we use for the development of assessments, although the development of three-dimensional assessments, it differs, from here a bit once we go through the unpacking. But it is a robust process that goes through extensive review, both by practitioners in the classroom and other researchers on the team, so that we can have a quality product. Here's just a quick overview of the units that we have in the interactions curriculum. I always say that interactions, it doesn't really have 4 units, it really has 6 parts. And the reason why I say that is because we as a research team defined a unit as all the stuff that we needed to have to be able to explain a phenomena. And as you might be familiar, not all phenomena are created equal or created to be able to be complete in a marking period. And so as we moved along, what we realized was that our units 1 and 2 were very, very, very long, because they were helping students really develop rich foundational knowledge that they would use in later units. And so we later went back and split those units into parts. And then we were able to have pre and post assessments using our 3-dimensional items at the beginning and end of every unit part. So the unit parts are more similar in size, I would say, than the units. So unit 1 and 2 are really, really big. And unit 3 and 4 are smaller because students are drawing on a lot of that foundational knowledge that they've already developed. So you can see the driving question for each of those units, and some phenomena that they explore within the unit. And here we have performance expectations that students will be addressing as they move through the unit. I will share that when we were in development, we really selected the performance expectations that we felt really encompassed the bulk of what students were learning. And so there are likely some performance expectations that students do work toward during a unit that aren't addressed in this list. And so as you looked at the list, you might have noticed that there are performance expectations that show up kind of in multiple units. And the reason why is because we really view performance expectations not as something to be covered and checked off, but as something that has kind of deeper and deeper and deeper levels of depth and understanding as you go. And so it's really important for students to be able to revisit the same performance expectations with different phenomena or with different driving questions in mind to be able to really dig into the depth. And so this graphic actually comes from a group of high school teachers that we worked with who piloted the interactions curriculum with us from the very beginning. They presented at the National Science Teachers Association meeting. And they developed this graphic to show how it wasn't even just in interactions where students were revisiting these similar performance expectations, but also then students would dig even deeper into these same performance expectations when they went into 11th grade chemistry or even AP chemistry. So students were continuously sort of cycling through these performance expectations. So I just wanted to share that with you. Part of our curriculum was to develop what we called educative teacher materials. So we really want our teacher guides to support teachers in developing a deep understanding of the next generation science standards, in case this is the first time teachers were really engaging with 3 dimensions or 3-dimensional performance expectations and learning goals. So you'll see in Unit 1 particularly, our teacher guides are really, really long. We tried to unpack for teachers exactly what's included in the unit, to list common talk prompts that they could use with their students. As we did research in classrooms and we heard things that students were saying and watched teachers sometimes struggle with how to respond, we would write those sample student responses and suggested teacher responses like into the teacher guides, so that even a first-year teacher could go through this and feel like they had really robust support in using the curriculum in their class. So what this ended up being as a teacher guide, where the teacher guides contain all of these scaffolds and supports and all of the student materials within them. For all 4 units, it ended up being more than 800 pages of support for teachers. However, with all of that in mind, we didn't intend at all for this to be a script, but rather a support for those who needed the extra support in their initial implementation. And really what we see as we've done research in classrooms is that different teachers use this really differently. So there are veteran teachers who have spent a long career with talk moves that will, pay attention in some areas and skip other areas. So, it's there for your use, but you don't have to read it like a script. But we also say that even though we developed these robust teacher materials, it's not really a standalone product. Engaging with a professional learning community and some kind of sustained learning team is really, really important for successful implementation of interaction. Okay, so an example unit, I wanted to just walk a little bit through our Unit 1, which is why do some clothes stick together when they come out of the dryer? This actually was our first unit, had been tested in classrooms for 4 years and revised based on feedback from teachers, revised based on what we were seeing in students' assessment items. At one point, we even completely reorganized and rewrote our Unit 1. And then when the project was over, we submitted it to the Achieve peer review panel. And we were really proud that we were the first unit to receive the digital design badge for high quality NGSS design for our Unit 1. And so again, the overarching phenomena is, why do some clothes stick together when they come out of the dryer? So when you pull them out of the dryer, why sometimes is there a shirt with like a sock stuck to it or something like that? And this really moves then into students thinking about how things like move together or pull apart. So they're really exploring electrostatics. And so as we move into the unit, one of the sub-phenomena or smaller phenomena that we tackled to get at this larger problem of why do some clothes stick together when they come out of the dryer is the pipe hands on the Van de Graaff generator. And so if you've not seen this demo before, you can look in the curriculum, but essentially if you plug in the Van de Graaff generator, it will start to build up charge. The charge will move to the pie plates. And then once the pie plates and the Van de Graaff have the same charge, they will repel off the top and kind of blow off the top of it. And so early on, students are asked to develop models of the pie pans on the Van de Graaff generator, and they revisit the same phenomena kind of over and over again throughout the unit. But each time, they're able to add more and more detail based on what they explored in these subsequent lessons or investigations. So this might be an example of students' first Van de Graaff picture with the pie pans. This was taken from a student who went through this curriculum after its many revisions. And so they would do this really early on, right after they saw this first demonstration, but then they move through some lessons to explore why that might happen. And so they move into looking at what are some patterns and how things push apart or stick together. What effect charged objects have on uncharged objects? How do I know if something is positive or negative? Things like that. And so during their exploration, when they're asked to come back to this, they're then able to add more detail. So this next model, they are then able to really think about, oh, there's some kind of electricity or humming that I hear, and I know that gravity is pulling on the pie pan, so they're able to add in those force arrows. So they're starting to get at what is the invisible or submicroscopic cause that's making this happen. What's the causal mechanism, is what we say. And then as they continue to move and start to think about charges, we now start to see common charges on both the Van de Graaff and the pie pans. So they're thinking about this as like expressing a net charge. And as they move even further through the unit, they now have a deeper understanding that actually the Van de Graaff and pie pans really have positives and negatives in them, and that there's an imbalance of these that cause the overall net charge, where they'll see their phenomena happening. And so at this point, you're probably thinking, well, what does this have to do with clothes sticking, together when they come out of the dryer? And so kind of the final artifact that students develop after they've gone through this unit is taking everything they've learned with the pie pans, really thinking about what's happening with clothes in the dryer and developing an overall model for that. And again, this is a really long unit. Students end this unit with really developing a robust model of the atom and a model of how charged and non-charged objects interact, which they then use throughout the rest of the curriculum. So I just want to talk a little bit about research results from the interactions project. Again, we wanted to support this model curricular materials to support students in bridging the things that they cannot see that cause observable phenomena. And so we examined this really in a lot of different ways to try to triangulate what was happening with this new curriculum. So we wanted to look at student understanding when they developed and revised models. We also spent a lot of time developing and validating three-dimensional learning progressions. We examined factors that impacted teacher learning and transition to NGSS in this early time of implementation. And then we worked with school and district partners to assess and revise implementation based on what their students learned. So one of the first research items to come out of this was really looking at student models and how they were able to revise them in greater detail over time. But what Dr. Mayer found as she did her research on student models was that when students were able to support their drawing of a model with either a written explanation or an oral discussion, they were able to really show a lot greater depth of understanding than just drawing a picture alone. And so we used this research to go back into the curriculum and make sure that all of our models allowed students to include a written explanation or encourage teachers to include oral explanations with their student models. That was a really important aspect of our curriculum work and development. The second kind of research to come out of the interactions project was the development of learning progressions for our three-dimensional assessments that really then drove our curriculum development and revision as well. And these learning progressions, if you've seen the Next Generation Science Standards and looked at how student learning progresses, for example, from kindergarten to 12th grade, the learning progression and interactions, it looks similar to this, except we're focusing in really, really, really deep into that 9-12 region. And we're looking at within this 9-12, where do students start and where do they end up? And the hope was to identify places where we could see where students were stuck and suggest for teachers the kinds of experiences to provide their students to help them move to the next level of understanding. And you don't need to look at all of this, but this is early development of one of these learning progressions that came from that assessment work. And we are actually still doing work on these learning progressions for physical science performance expectations. We also looked at how teachers transition to implementation of three-dimensional teaching in their classroom and really supported students. And we looked at teachers developing their own learning goals as part of a professional learning program and tracked how they worked towards their learning goals over time and what that looked like in their classroom. And it was really interesting to see that essentially different teachers took very different approaches to meeting their learning goals. So I had one teacher that took sort of an action research approach, really wanted the driving question board and eliciting questions from students to be the focus, and really tried out different things that he was reading about in the literature in his classroom and tweaked them over time to meet the needs of his unique students and classrooms. And I had another teacher who was really focused on supporting student collaboration through talk, particularly around the use of evidence to support their discussions and their claims. And how this teacher went about supporting his learning was really focusing on collaborating over time in our professional learning communities to support that work with his students. So he really tried out different things that he had talked with his instructional coach about, and maybe one-on-one with some of his other teachers to come up with these changes in his instruction that were well-lasting. And finally, we also did some quantitative work of the student testing data, although we didn't have a lot of it to make really broad claims about what the interactions curriculum could do, but we're seeking additional funding to do deeper tests on this. But our early quantitative examinations of student test results had really promising indicators. The most promising being that when we looked at interactions classrooms where teachers were using all of the practices that we hoped they would use, because we supported those both in the development of our materials and through our professional learning program. When we looked at those students' test scores, we couldn't see any variation in those scores by race or gender. And the only way that we saw variation in student test scores with interactions was by comparing it to how well really the teachers engaged in three-dimensional instruction as promoted in our professional learning program and in the materials. So that's really promising results, but again, we're seeking additional funding to do some more research in that area. We also supported teachers and districts in collecting their own results. And so this is from a classroom in Michigan where they collected their AP testing data as they implemented interactions and some other curricula that we have and create over time. And so you can see how their multiple choice and their free response AP test scores changed over time, which this school really attributes to the focus on three-dimensional learning in physical science and in chemistry that they did in conjunction with our team. And so hopefully that gives you a really good background on the interactions project, how we developed the curriculum, what a unit looks like, what research came out of that curriculum. Again, I'm happy to answer more specific questions about any of that stuff anytime. You can email me whenever. But what I hope that you get out of this presentation is that you know that interactions is a high quality full year curriculum that can be used at 9th or 10th grade. The implementation of the next generation science standards, it does require teachers to shift instruction. And research does suggest that it can take 3 to 5 years of sustained support. So our hope is for classrooms where interactions will fit, that this could be like one aspect of the support for teachers to make this shift. And that students engaging with interactions materials are able to develop really deep understanding of these observable phenomena and explanatory models of causal submicroscopic interactions, something that, again, early research out of Michigan State University showed that even undergraduate students really struggled with. And so if we can use this curriculum to support students in doing this at 9th grade, it'd be really exciting to see where they go from here. So just know that, again, it's all free online at learn.concord.org/interactions. You can make a free teacher account, look at all the teacher guides, all the student materials, all the assessments. You can email me if you want access to the rubrics, which we have not yet posted online and we probably won't, but I can give them to you directly. And if you have any additional questions, please email me, Gerber, like the baby food, GERBERAN @msu.edu. I'm also on Twitter, although not very much, but you're welcome to follow and we can communicate there as well. And I hope this has been helpful. So thank you so much for listening, and I look forward to talking with you more about using interactions in your school. Thanks.